So next topic, heterocyclic chemistry. So first I talk about the pyridine because pyridine is important in examination point of view. So in pyridine also we have electrophilic substitution reactions and nucleophilic substitution reactions. So these things we talk first. First we'll go for the electrophilic substitution reactions. So in the pyridine we have 5 carbons. So this will be 1 2 3 4 5 6. So 2 and 6th positions are same, 3 and 5th positions are same, and 4th position is unique position. Okay, and the electrophile, where electrophile goes. So first there are 3 possibilities: C2, C3 and C4. So electrophile can go and attack to the C2, C3 and C4 positions. So which position will be major, we'll see now. So when we have a C2 position, imagine that the electrophile attacks to the C2 position. In such case, this bond has to go like this because there should be a negative charge for electrophile. And now here negative charge is coming, and then here positive charge comes. So now electrophile comes and attacks to this. Okay, once this electrophile attacks here, what will happen? This bond goes here and this bond comes here, and then here positive charge comes. This is at C2 position. Then we'll go for C3 position. At C3 position, so the bond has to come this way. So this is C4. So now there is a positive charge here, and the electrophile comes and attacks here, and this goes this way, and now there is a positive charge on nitrogen now, and this bond comes here, this is the at C4. And last we have a C3 position. C3 position will be like this. If it comes this way, negative charge here and positive charges here. So electrophile attacks to this. Now this bond goes here, and here positive charge, and this bonds comes here, and here positive charge. So when we are talking about C3 position, so the only difference here we can see that, see, in a C2 position, C2 attack, there is a positive charge on nitrogen, and at C4 also there is a positive charge on nitrogen, but at C3 there is no positive charge on the nitrogen. So because of that, the electrophilic substitution reaction preferably takes place in the pyridine at a C3 position. So why it's not taking place in C2 and C4? Because when we saw the pyridine MOT diagram, so what will happen here, we have a 6 pi electrons, okay, excluding this lone pair and nitrogen. So if you see the MOT diagram, these things will not be in the neutral, like when we have homoatopic molecule, the orbitals will be having a same energy. But when we have a one more electronegative atom, one less electronegative atom, in such cases what will happen? So they will not be having a alignment. Okay, so because of that reason, most of the electron density resides on the nitrogen. Okay, so when we have positive charge on this nitrogen, and it further pulls the electron density from the ring. Not generally the pyridine is a not that electron rich. So electrophilic substitution reactions takes place in a drastic conditions for pyridine. So when we have a positive charge on nitrogen, further it takes electron density from these carbons, and this is making a ring is more electron deficient. In such cases, electrophilic substitution reactions will not take place. So only in case of C3 there is no positive charge on the nitrogen, and because of that reason the electrophilic substitution reaction preferably takes it at C3 position for pyridine. Okay, I hope it's clear. So and then we have a effect of substituents on pyridine. Effect of substituents. So when we have a NH2, okay, so we know that NH2 is the ortho meta directing group, right? So when we treat this compound with H2SO4 and HNO3, here we are doing a nitration. Okay, so when we have a pyridine and 2 amino pyridine, so which one will be more reactive towards electrophilic substitution reactions? So this will be more reactive towards electrophilic substitution reactions, because here we have NH2, it gives electron density to the pyridine ring. So now we have a ortho meta para, so this goes to the 5th position. NO2 goes to the 5th position. Here NH2 and then here NO2. And when we have a simply this compound, now NH2 is at a 3rd position, so same nitration we are doing. In such cases we have a ortho meta para. So here it takes this position and this position, so this is ortho and this is also ortho, and here the electrophile goes to the ortho position, that is this position, the electrophile goes NO2. Okay, and why this is not going to this position? Because so this nitrogen is taking, means this NH2 is the electron releasing group and it is giving electron density to the nitrogen, and compared to this carbon, this will be having a more electron density. Because of that reason NO2 is going to a C2 position. And now we have NH2 is at a 4th position. So here the product will be this one. Okay, so when we have a amino group, NH2 group, in such cases the product will be it goes to the ortho and para positions. And when we have a methyl group like this, in this case in case of benzene, if you see the benzene case, when we have a methyl group, so this also acts as a ortho para activator, but in case of pyridine it will not show any kind of directing capacity. Okay, so this is purely the reactant, means like the methyl group doesn't have any role in this. So when we do a nitration or sulfonation on this, so we'll get this compound. So this group is a meta to methyl group, but here methyl group doesn't have any role. The only NH2 group in case of pyridine can direct the groups to the ortho and para position, but methyl group can't. And this and then we have the reactivity order. If you see the reactivity order of benzene and nitrobenzene and pyridine, so here the benzene is a more reactive, to nitrobenzene is more reactive compared to the pyridine. So in case if we see the pyridine, if you see the nitrobenzene, this is not that reactive towards electrophilic substitution reactions, because the nitrogen, the NO2 group is an electron withdrawing group. It takes electron density from the benzene. Because of that, it's not that reactive towards electrophilic substitution reactions. Imagine that the pyridine is less reactive than this one, so we have to use more drastic conditions for pyridine compared to this nitrobenzene. And in case of when we are doing a pyridine reactions, in those cases we can't use acid catalyst. So why we can't use acid catalyst? If we use acid catalyst, the H plus goes and binds to this nitrogen, and now it become NH plus. Okay, now the nitrogen is having a positive charge. What will happens? This is electron deficient, and it further takes electron density from the remaining 5 carbons, and now this is becoming a more electron deficient. If this becomes more electron deficient, the reaction doesn't take place. Okay, so these are the some points you have to remember about pyridine. And next there are many other reactions for pyridine, nucleophilic substitution reactions, and some of the electrophilic substitution reactions, and we'll see those reactions in the next lecture. And if you like my video, please subscribe to my channel, and also please forward to your friends. You can, if you have any doubts, you can write in the comment box. Thank you.